All right, so on this one here, we got the instructions. They say to find dy dx, that's the derivative of y with respect to x, at x equals 1. So that's a slope at a point. Slope at a point. We have this equation given, y squared plus x plus 2xy. So first thing you'll notice is it's not solved for y, is it? Mm-mm. Can we solve it for y as a single equation? Probably not, because there's a y and a y squared. So I could use like the quadratic formula or something and get like a plus and a minus version. Yucky, yucky, gross, gross. But here's the thing. Remember, if it has an x and a y in it, that means the derivative usually has an x and a y in it, which means, as we saw in the dinosaur graph yesterday, I usually need more than just an x value to locate the actual value. So why did they only give me an x value here and not an ordered pair? Well, I don't know. Let's see. Based on what we did yesterday, if we are interested truly in just the slope at a point, it would be better to take the derivative, then plug in and then solve, right? Rather than take the derivative, solve, and then plug in. So let's see if we can at least do that first step, and then we'll see what else needs to be done as we get to it. So first thing I want to do is just take the derivative. Take the derivative of y with respect to x, and I'm going to do d dx out in front, right? And I don't know why I put dy dx. Okay, I was thinking explicit mode, right? Let me back up here. It's d dx colon, right? And then we take the derivative. Or we put d dx in front of both sides as a whole separate line, right? Let me do that. I haven't done that yet as a whole separate line, but mathematical purists would insist on doing it this way. Okay. So and that's really what we're saying when we put d dx colon, right? It substitutes that whole line. That line is not a bad thing to do if you have to like rewrite some of the terms anyway, like you have to put radicals as fractional exponents. It's not bad. But again, it's not required. If you put d dx colon, you're good. So what would be the derivative of y squared with respect to x? 2y to the first, right? Times the chain rule, dy dx, right? Plus, what would be the derivative of x with respect to x? 1, right? 1 dx dx, essentially. And then on the right-hand side, I've got a product rule. How many factors do I have there? What's the fewest I can have? I have 3, but I could group the 2 with the x, right? It's a constant multiple. So that would give me the fewest number, which is 2. So with 2 factors, I'm going to have 2 terms, right? So we'll take the derivative one at a time. The derivative of 2x with respect to x is 2 dx dx, which we don't need, times y goes along for the ride, plus 2x goes along for the ride. If you want to put parentheses to show association, you can. 2x goes along for the ride times the derivative of y, which is really 1, times the chain rule, dy dx. So there are a couple of accounting things in there to make sure we did it right. The product rule with 2 factors generates 2 terms, right? So that's good. The other thing accounting wise, remember, is you have 1, 2 y's. So you're going to have how many dy dx's? 2 dy dx's. Yeah. Oh, because it was the other guy's turn to take the derivative, right? The derivative with respect to x of fg is f prime g plus f g prime, and it's the f part. He got taken the derivative of in the first one, and then he's going along for the ride. This is f prime g plus f g prime. Okay. Yeah, for some reason, the product rule is the one that's the hardest for 23 years I've been teaching, and the product rule at any level is the one that is, for some reason, the hardest one to get students to do correctly every time. Okay, so yeah, so that takes care of the derivative, right? And now the algebra, we need to get the dy dx terms by themselves. So here's a dy dx term, there's a dy dx term. So I'm going to leave this guy on the left, and then I'm going to bring the other guy across, and it becomes minus 2y dy dx. and then equals, I got a 2y that's on the right-hand side, and now the plus 1 goes over to the other side and becomes a minus 1. So that's just like a shell game, right? We switch 2 terms. And now we can factor out the dy dx on the left. And that leaves us a 2y minus 2x. The right side is still good. And now we're round third, heading home. Balls in the outfield. We're going to score over the Astros. The game's tonight. But there's a unicorn game tonight, so I'll watch that instead. We divide through by what we're multiplying dy dx by. And it divides out on the left, and we're left with 2y minus 1 all over 2y minus 2x. So what I did there is I went against the rule of what I told y'all to do. I said to take the derivative and then plug in. But I was in algebra mode. This right here would be the derivative, yes? So let's go back and say I wanted to plug in there. I need more than just the x value, don't I? When x is 1, I can plug that in, but look, I still need to know the y value. There's 2 different occurrences of y, whether I do it up there in the beginning before I solved or at the end. So right now, in either step, the derivative step or the solving for dy dx step, I'm just sitting there, right? Can't do anything, just floating in the water. There's not even a current. Ugh. Lindley, you kind of look like the guy from the movie. You resemble him. Is that his name? Yes. Winnie? Linguini. Yes. The dude's name is Linguini? Yes. I've seen the movie and I didn't know that. I thought it was like Harold or something. All right. So here's the question. How in the heck are we going to find the y value when x is 1? How have we always found y values when we're given an x value? Plug it in, right? Plug it in. Now, normally it's solved for y. We got f of x equals, but it's not solved for y, but that's okay. We can plug it in. We'll see what happens. We're going to trust that if they give us x equals 1, there's up to 2 y values that it could be. If we end up with 2 y values, I guess we'll find the derivative twice. Okay, so to show that we're plugging it in, since it's not in function form, we just have to say something like at x equals 1, colon, right? And now we plug it in. We get 1 squared plus, I'm sorry, I'll get y squared, my bad. Y squared plus 1 equals 2 times 1 times y. All right, now if I solve, I'm going to have y squared minus 2y plus 1 equals 0. I have a y squared term and a y. Dang it. 3 terms, squared, non-squared constant equal to 0. Factor, right? And if it doesn't factor, we got the quadratic formula. Please factor, please factor. Y minus 1 times y plus 1. It's y minus 1 times y minus 1, right? Or y minus 1 squared. Oh, thank goodness. I see what College Board was doing. If there were 2 solutions, I wouldn't have known which one to use, right? But thank goodness there's only one solution to this, right? The graph is y minus 1 squared, which means it's going to bounce just like x squared bounces off the x-axis. This graph bounces off the y-axis. It's gonna look something like this. Boing. Okay. There's only one solution. All right. So now we have the point, right? We have the point 1, 1. So now we'll just do it both ways. If we're going to, if we'd already gotten down to this level here, now we would say dy dx at the point 1, 1. And then we plug it in. And we got to be careful, right? We plug in a 1 for y and a 1 for x. We don't want to get those backwards. I guess in this case, it wouldn't matter. Uh-oh, what's happening? 2 minus 1, that's 1 over 0. Crap. What happens when we get 1 over 0? It does not exist because it's some type of what? It's some type of infinity, okay? We're not going to put some type of infinity because we don't know if it's positive or negative infinity. What type of tangent line has a slope of infinity? because we're saying the slope is infinite. Vertical? Yeah. We have a vertical tangent line. And that is consistent with what I just said, right? The root was y minus 1 squared. So instead of bouncing off an x-axis, it's going to do this. So right there, it's where it turns around. And normally there would be two values of y. But in this case, there's only one. So that would be the answer. The answer would be some type of infinity or d and e. Now, if I were to do it up here, let's see what I get if I would have taken my own advice. If you would have taken the derivative and then been like, dang, I need the y value, then you would come over here and find the point. And instead of doing the algebra with the variables, you could then just say at the point 1, 1, and then you'd plug in and you would get 2 times 1 times dy dx plus 1 equals 2 times 1 plus 2 times 1 dy dx. And now look what happens. What happens with your 2 dy dx's? They cancel from both sides, don't they? And you're left with 1 equals 2. Oh, don't it though? Oh, sometimes it's like that. What happens if you did this in algebra when your variables go away and you end up with a non-true solution? A non-true statement? This is a contradiction. And we show that by 2 ramming arrows, like 2 rams butting horns. What does that mean? Y'all remember from algebra 2? No solution? All right. There's no solution, or the solution does not exist, right? Or D and E. So it looks a little bit different, depending on how far you go. But it's the same result if you interpret it correctly. Okay. So that's an interesting one. Hey, just to review, what happens if you work down in a conditional equation and you end up with like 3 equals 3, a true statement? What's that? All real numbers. Good. This is called an identity. And the solution is all real numbers. Okay. It's true for every value in the domain. So those are the 2 cases. What if you ended up with another true statement, like you get down and your variables go away and you end up with something like this? That's another identity, right? That means all real numbers. So anytime you end up with a true statement at the end, right? It's all real numbers. Yeah. All right. There's about 8 dum-dums left in here. I'll go pick up the pink slips for them during lunch. No dum-dums in this class, right? Right, Linguini? Yeah. I mean, you're tall like he is. You're stringy, linguini-ish like he is, right? And you're even wearing like a baker's outfit or a chef's suit like he is. Yeah. If only you had a rat. That's a therapeutics code. This guy took it. Yeah, I saw that. Okay. All right. Any questions on the warm-up? Are you warm? Feels good. Who likes implicit differentiation? Yeah, that's what I thought. There you go. There you go. There, yeah. Father, yeah. Yeah. Yeah, there you go. It's fun. You just got to remember that when you take the derivative with respect to x, every variable that's not x, right now it's just y, gets a d variable dx. Okay. Look what you could do. Let's do it like an intermission here. Intermission. What if I have something like this? 3y squared plus 2x squared plus 7 sine of z. That's right, z minus 4 x to the 1, or not x to the 1/2, 4 p to the 1/2 minus h equals equals 11. Linguini's a funny name, but someone this morning in my first period was dressed up like 11. Not the number 11, but that show 11 from the Stranger Things. Yeah. It was Natalia Diaz. Yeah. And I just like, who are you? She goes, 11. And I'm like, no, not how old are you? Who are you? And so I didn't know that the girl's name was 11. Parents are getting pretty creative these days, right? Yeah. Oh, see, I haven't even seen the show. I didn't know if her birth certificate said 11. Right? Yeah. Okay. So look at this. We have 1, 2, 3, 4. We have 5 different variables in here, right? Look, we could take the derivative with respect to pick a variable that's in there. Z. Okay. Right. In the real world, there's usually several variables in any equation, right? You tinker with one of them at a time, though, to see how everything else is affected, right? So that's what we could do. Let's take the derivative of this equation with respect to Z. So here's what it would look like. It would be 6y to the first times, guess what? dy dz plus, that's my Z, yeah, plus 4x to the first times dx dz, yeah, plus 7 cosine of z times dz dz. Do we need that one though? No, it's the only one that we don't need. Z minus 2p to the negative 1/2 dp dz, and then minus the derivative of h is 1 times the chain rule dh dz, and then any constant with respect to any variable doesn't change. So notice we had 1, 2, 3, 4, 5 variables there. Because I took the derivative with respect to one of them only, 5 different variables, I have 4 d variable dz's. Okay, yeah. Oh, yeah, sorry, dz. Yeah, I got real lazy there with my brain. It always happens at the end. Thank you. I didn't mean that. What's that? It's a constant. Yeah, it goes to 0. Yeah. Now, you think that's cool that we take a derivative with respect to z. Watch this. Let's come back and take derivative of the original thing with respect to t. Are there even any t's in the equation? No, no big deal. No big deal. We get 6y times dy dt. Yeah, plus 4x to the first times dx dt, plus 7 sine of z times cosine. Gosh dang it, I'm a doofus. I'm the dum-dum. I need to jump in the barrel. dz dt. dz dt, isn't that the place in Seguin where you can go play? Yeah, yeah. Minus 2p to the negative 1/2 dp dt, and then minus dh dt, and then still equals 0. Yeah, so believe it or not, you could take the derivative with respect to an equation using a variable that's not even there. So if you understand those 2 examples, then you understand implicit differentiation, right? Okay, sweet. All right, let's come down here. This example number 6 was the segue into this type of question. If you ever get a derivative that's a quotient of 2 variables, okay, your derivative is a quotient, then you're going to have 3 different cases, all right? When the top only is 0, when only the numerator is 0, you get 0, right? 0 divided by 5 is 0. 0 divided by 10 is 0. What type of line has a slope of 0? A horizontal tangent line. So if you want to know where the horizontal tangent lines are and you have a quotient, set the numerator of the derivative equal to 0.
Whenever you told that you probably won't be there till 12:35, that meeting.
Yeah.
But I forgot to tell you why we were there. Hey, Barbara, how are you?
No. Is it lunch yet?
Yeah, probably.
Oh, okay. Oh.
But it's just because the district's, I think, in a purchase at Desmo,
Uh-huh.
and she wanted, and Huey wanted to know how it's going to affect Kim Huey, how it's going to affect AP and SAT, like if all the kids are using the calculator. So she asked us if we could just jump in just to kind of.
Okay.
But you don't have to quit what you're doing.
Yeah. Okay.
You're good.
All right. All right. So when just the numerator is 0, we get 0, right? And that's a horizontal tangent. as we just saw up above, when only the denominator is zero, you get a slope that's either positive infinity or negative infinity, okay? And that's going to be a vertical tangent because that's the slope of a vertical line. Now, if you happen to get 0 over 0, 0 over 0 has no tangent line, okay? It's not vertical, it's not horizontal. So if you end up with a value that makes both the numerator and denominator 0, you throw it out. What that's going to look like is this. I'll show you what it looks like. It looks something like, we're going to study cardioids and limicons later in the year. You're going to get a function that kind of looks like this. It looks like, in fact, Mason drew one yesterday. It's called a cardioid. Oh, you do? Yeah, it's called a cardioid. All right. The limicon is like the snails that you saw. I'm not cool like that. And his name is Max.